Okay, so welcome to this talk today given by Leonardo Aguirre. He comes from EABAC, from the Department of Fish Ecology and Evolution.
Yes.
In Switzerland. He studied mathematics at the ETH. Then he did a PhD also on mathematics there at the ETH about Gaussian subalgebras.
Yes, mathematical physics of quantum integrable systems.
Okay, and something that I saw one paper of yours was something called wonderful models,
Yeah, right.
which I don't know what it is,
colorful.
But it sounds great.
it's the fixed term for that, but it's quite colorful.
Yeah. And so then he decided to apply his knowledge on ecological problems, and so he's doing a postdoc with Carlos Melian there at EABAC, where as far as I know he's trying to bring all these kind of hardcore mathematical concepts and try to bridge between individual interactions and mesoscale descriptions of ecological systems, where he tries to bring this in common. In the end, the idea I think it would be to mix with experiments or experimental designs.
Yes,
and I think he will talk to us about his ongoing work on this field. So the floor is yours.
Thank you. Okay, hello everyone. Welcome to this talk about identifiability and prediction in ecological interaction network models. Today I will talk about a rather broad class of individual-based mesoscopic ecological models and discuss the topic whether they lend themselves to predictive or to prediction, or whether they make for good predictive models. The theoretical ecology community knows partial answers to this question for various case studies, but there's, as of now, not a general framework that allows to assess whether one of these models, called Markovian interaction networks, can make for a good predictive model. So let's have an overview. First, I'll give a few words about the scientific method and the status of predictive ecology during the last decades. Then I'll introduce mesoscopic population models and jump right away to Markovian interaction networks as a specific subclass of them. I'll discuss the connection with the classical ODE formalism, and then I'll also give a few examples. Then I'll move to the main topic, prediction and parameter estimation for Markovian interaction networks. And finally, I'll discuss a current project of mine where I try to build a software platform in Python that allows to assess prediction and identifiability for this model class. So let's first talk a bit about, as an introduction, about the scientific method and predictive ecology. So the old tension between practice and theory was taken up by Wiener in 1995 when he notes on the practice of ecology that there seems to be a centrifugal force in ecology that keeps theory and data far apart from each other and from what we are trying to understand. He then goes on in stating that what we are trying to understand are indeed the old questions of natural history. And he also notes that there seems to be a deep-rooted tradition in ecology that encourages exploratory data collection and classification, but at the expense of investment into a solid scientific method, and including building of mechanistic models and their validation. So Hulan and others come to a similar verdict in 2017 when they note on the priority of prediction in ecological understanding that prediction is the only objective way to demonstrate scientific understanding of the natural world. The implicit criticism being that in the current ecological community, prediction and understanding often seem to be two separate objectives. And the community seems to be split between theoretical and practical ecologists, each following the logic of their own subdiscipline, which effectively means that the relation between data and theory is often a matter of narrative. So this the main goal of this talk is to see how this situation is for mesoscopic models, and to show a way out of it, a possible way out of it. So what is the situation today? In theoretical population ecology, there's a plethora of conjectured population dynamics and mechanisms. These two article covers are representative of it. There are, for example, red-queen dynamics, which is a broad term referring to a kind of dynamics that should enable continuously repeated arms races between taxa. And another example would be noise-induced bistability, which is a phenomenon where a classically stable fixed point is perturbed into a bimodal distribution. Now, the details are not important at this point. We will return to these examples later in the talk. But for now, let's note that these two phenomena are examples of a mode of research where model simulations are related to actual experiments only in a rather informal way. So this begs the question, can these models ever be tested? Of course, this question calls for a whole lot of practical considerations, but there might be also theoretical obstacles to testability. And indeed, from a theoretical standpoint, it boils down to state and parameter estimability. So suppose that a data series, an observation data series, comes not from nature, but from the model itself. Would it then at least be possible to reconstruct parameters and the current states of the model? While this seems like a bit of an academic question, it has major ramifications for experimental design, because a negative answer could be used to preemptively exclude certain models before precious financial resources are invested into experimental trials. So state and parameter estimability is a well-developed topic in the macroscopic ODE setting and has led to numerous experimental design protocols there. But on the other hand, it is relatively uncommon for mesoscopic individual-based models. And the goal of this talk is to discuss what would be required to build an analogous framework in this setting. So let's delve into mesoscopic population models then. Evidently, nature can be modeled at various scales, and mesoscopic population models are an example of this. So for population models in general, for individual-based population models, one could start at the microscopic level and model individuals as individual agents that are able to move in a spatial environment and have different traits that can also change over time. In this way, one would end up with a stochastic agent-based simulation. And as you surely know, there have been interesting phenomena explored in this way, where referring, for example, to pattern formation or emergence of collective behavior. But these agent-based simulations are usually analytically intractable, and in particular, prediction is infeasible for them because they have many unobservable degrees of freedom, and it would never be possible to bring, so to speak, nature and the model in the same state as a prerequisite for prediction. So one simplification that can be made is to subdivide the different agents with all of their traits into a finite set of taxa, and to assume that they are part of a well-mixed aggregate. We will later talk about whether these conditions are reasonable or under which circumstances they might be reasonable. Anyway, what one ends up with is what I call a mesoscopic model. So its states are accounts of finite abundances of the different taxa, and its dynamics proceeds by stochastic jumps between these abundant states. Computational forward simulation remains easy, but prediction is much harder, but it seems not impossible. We will touch upon that later. But first, let's fix the basic structure of a mesoscopic model here in more formal terms. So we consider a continuous time set and a finite set of taxa I. This means that the abundant states in the population of these taxa form a hypercubic lattice X in the non-negative orthant of the respective real space. And each transition corresponds to a transition vector that maps this lattice to itself. So for example, here in the two-dimensional example, the first taxa is increased by 1 to this transition. In this transition, the second taxa is decreased by 1, and in this transition, 1 taxa is decreased and 1 is increased. We will later talk about biological interpretations of such transitions. The timing of these jumps between abundant states is governed by a continuous time Markov chain, also known as jump Markov process, with intensity functions Fr. This means that state transition happen at random jump times TL, whose intervening holding times are distributed exponentially with decay parameter F0 being the sum of the intensity functions. And when a transition happens, it happens according to the embedded discrete time Markov chain XTL, which means that when a transition happens, it happens, the rth transition happens according to this probability Fr divided by F0 evaluated at the current state. So those are the rules of a continuous time Markov chain in general. Let's now discuss whether these models are even reasonable. So there are two things that, apart from the finite taxa assumption, of course, there are two things that need to happen on a faster time scale than the typical dynamics of the model for it to be reasonable. First, the physical events corresponding to transition need to happen fast. As for two transitions to not overlap in time, or at least for that to be unlikely that they overlap in time. The second condition is a bit more crucial. It means, or anyway, more controversial. It's the well mixing assumption. So they have to be a part of a well mixed aggregate in this framework, simply because the encounter probabilities between individuals are implicitly encoded in the intensity functions as averages. And for these averages to be representative of actual encounter probabilities, there needs to be spatial homogeneity. So the classical example where we have such well mixing is a container of gas shown on the left. Here the well mixing is established by itself through the Maxwell-Boltzmann velocity distribution of molecules. Then moving to ecological settings, like for example, in an aquatic microbial environment, it is rather unlikely that well mixing happens on very large scales. But there is merit to the argument that it at least happens locally. So possibly these models can work as local building blocks for larger aquatic ecosystems. Then lastly, maybe leaving the ecological context a bit, these models have also been applied in the social sciences, particularly relating to social networks. And also here it seems they seem most appropriately used where in tightly interconnected clusters where there is, in a sense, well mixing, where every node is connected to almost to every other one. So let's now look at the subclass of these models. The subclass of these models called Markovian interaction networks. This is a very versatile subclass, and it's because its transitions are particularly intuitive. They correspond to interactions between individuals. So here we have a few examples of these. I visualized every interaction with its bipartite directed graph. So the interactions are visualized by square nodes and the taxa by round nodes. So in the first external source or immigration interaction, one individual of taxon I is introduced into the well-mixed system. To the interaction in the death interaction below, one leaves through this interaction. In reproduction, M equals 1 or 2 individuals reproduce in that they produce an offspring. And in the same way, we can frame competition, parasitism, commensalism, mutualism, and even copying group behavior at the bottom row where in a sense M individuals of taxon J convince one individual of taxon I to join their taxon, where taxon here stands for behavioral dispositions. Then we also noted the translation vectors corresponding to this, where EI is simply the ith standard basis vector in the state space. And for completeness, in the last column, we noted the often used mass action intensity functions, which have a rate constant CR and are otherwise proportional to the number of possibilities to draw the respective number of ingoing individuals of the interaction from the pool of individuals at the current abundance state. And then there's also the scaling parameter K, which speaks for the fact that when the system volume becomes larger at a given abundance state, interactions will be more unlikely. So it incorporates the respective scaling. Mm-hmm. So these square nodes, this is the interaction. So this means that one individual of taxon I goes into the interaction, and the edge labels mean how many individuals enter into it. So yes. So here, in asexual reproduction, 1m equals 1 individual enters the interaction, and okay, perfect. So now here we see how these interactions can be composed into more complex graphs. In the first row, we have an example of a very simplistic predator-prey network, where the predator taxon can reproduce asexually. The predator taxon can die spontaneously, and there is an interaction where a prey individual gets consumed by a predator individual, and the predator individual reproduces in the same instance. This is a bit simplistic, but it will serve to make a point later. So in the second row, we have another example that was studied in the literature from a theoretical and practical point of view to study stochastic bistability in an ant colony. So here the two round nodes, the taxa, so to speak, are behavioral dispositions. Namely, ants, when they leave the nest, can take one of two possible paths in that experiment, and ants with behavior 2 can convince an ant with behavior 1 to join their behavior and change the path by interaction 1, for example. Interaction 2 is the reverse process, where behavior 2 is changed into behavior 1, and interactions 3 and 4 are simply spontaneous switches of behavior. In the last row, we have a even more elaborate network. So here, this has been illustrated. This has been taken out of many literature sources by an overview article in 2020, where this has been seen to be representative of many eco-evolutionary models that should illustrate red queen dynamics, meaning the repetitive arms races between different taxa brought about by negative frequency dependent selection. So we have two species, a host species and a parasite species. Each has two phenotypes, and host phenotypes can reproduce asexually as before. The parasites can die spontaneously. The hosts can compete with each other in interactions 3 through 6, and host 1 can interact with parasite 1 either by the parasite can kill the host in the interaction, or the host can the parasite can leave the host alive and reproduce through it. So we will later see the dynamics that can arise in this fashion. Yes, yes. We can look it up later. I'll have it on the hard disk. So let's now first make the contact with predator-prey trajectory with the classical ODE formalism. with help of the first predator-prey system. So here we displayed trajectories for different system sizes, and we can clearly see that when we increase the system volume, indicated here below, the trajectories become more regular, and for large system sizes, they are very reminiscent of the classical periodic trajectories of the Lotka-Volterra model. This is no coincidence, but a manifestation of a general fact. Namely, if we consider concentration variables x tilde I, then a scaling limit of the stochastic dynamics is given by this ODE here. So the VR are still the transition vectors of the stochastic model, and the F tilde R are the deterministic kinetic laws corresponding to the intensity functions at play. So, for example, for the mass action stochastic kinetics, this is the deterministic mass action kinetics that is commonly used, with MI being the number of taxon I individuals entering the interaction. So this is where most applied ecology studies, or many, not most, but certainly many applied ecology studies draw from, and they usually appeal to this classical theorem of Kurtz from 1970 by outlining the individual interactions in a rather informal way, and then jumping to the macroscopic scaling limit by saying that for a fixed time larger than 0 and probability p smaller than 0, there is a system size k large enough so that the stochastic trajectories will stay close to macroscopic trajectories in the time interval from 0 to t, with probability lower bounded by p. However, this theorem says nothing about what happens after this time horizon t, and indeed for a given system size, the time horizon can be rather short. So over longer time spans, the behavior can be dramatically different between mesoscopic and macroscopic models. So let's have an overview over what the differences are. In the macroscopic case, the dynamics usually preserves the positive orthant of concentration state space. It usually contains attractors to which in the long term the dynamics converges. In simple cases, these can be attractive fixed points or limit cycles. Either way, when the system exhibits a fixed point, then the local behavior around it can be investigated using the linear stability analysis. And there's usually a stationary distribution on the attractor subset, also known as invariant measure in dynamical systems theory. In the mesoscopic case, however, the situation is quite different. First of all, there can be stochastic extinction at the boundary. So if the interactions permit it, that a taxon dies out and cannot come back, for example, by a mutation from other taxa, then the trajectory will be absorbed at the boundary of the state space, and with probability 1 in finite time, and this happens. So the stationary distribution, if it exists, is supported on the extinction subset, which often makes it rather uninteresting. For example, if every taxon can die out, then every taxon will die out in the long run with probability 1. And we have as a new concept the extinction time distribution, which is the distribution of times until extinction or until the absorbing boundary is reached from some given initial state. But it has to be noted that for decently sized systems, the extinction times according to this distribution can be extremely large sometimes, and there's interesting behavior before that happens. Indeed, before extinctions, such a model can behave just like a stationary model, and the distribution according to which the states are on average visited is called the quasi-stationary distribution, which is simply the distribution of time averaged mean occupation times conditional on non-extinction. Another new concept here is that of stochastic amplification. So there's the fixed points of the macroscopic limit models are usually turned into noisy fixed points, which means that the dynamics fluctuates around them. And this also enables stochastic switching in the case where there are several fixed points in the macroscopic model. Similarly, cycles of the macroscopic model are perturbed into noisy cycles. But even more interestingly, it can happen that the macroscopic model has one attractive fixed point, but this gets perturbed in a non-trivial quasi-stationary distribution. And this means in particular that linear stability analysis is now insufficient even locally around the fixed point of the deterministic limit model. We will now see the examples of this, namely the ones that we looked at before. So this is the ant example. Here the quasi-stationary, here this has a non-trivial stationary distribution because the ants can change behavior spontaneously. No behavior can die out in that sense. And note that the distribution is supported on this line segment because the total number of ants is conserved. And the stationary distribution is supported here at the ends of the line segment or towards the ends. On the other hand, the deterministic limit has an attractive attracting fixed point here in the middle. So the behaviors are dramatically different in the deterministic limit. The ants will usually equally distribute between the two paths, and in the stochastic model, the ants will predominantly change one of the two paths as a group, and then at some time switch to the other preferred path. Even more interestingly, in the specific parasitism example of before, this has also a single stationary or a single attracting fixed point in the deterministic limit, but this gets perturbed into a very complicated quasi-stationary distribution in the mesoscopic model. So note that the state space is four-dimensional here, so we need to take two-dimensional projections to visualize it. Here, for example, it is projected to the space where both parasite phenotypes are aggregated and counted on this axis, and here the host species abundance is counted, and in this plot here only the parasite taxa are counted. So this also immediately raises can make for some ecological hypotheses. For example, here, if one were just to know host and parasite abundances as aggregated, then it would seem that they rarely die out because they never get close to the boundary. However, what's the case is that parasite type 2 often gets close to the boundary, but parasite type 1 does not. So this certainly makes for some interesting hypotheses, but we'll not delve on them so long because we would like to outline a general method that allows to investigate these scenarios for any given Markovian interaction network. So when I started investigating these models about a year ago, I noted at this point that pretty much all theoretical studies about these kinds of things end at this point with the quasi-stationary or stationary distribution, and never ask one question that seemed very obvious to me. Can the dynamics inside the quasi-stationary distribution actually be predicted from observations? And this talk should basically outline a strategy how this could be achieved for an arbitrary given Markovian interaction network. So let's turn now to this question, prediction and parameter estimation. So first, one could ask, why is this question not more often asked? And I think the issue is twofold. With one part, tying in with the discussion we had in the beginning about the cultural issues in ecology. So about the splitting of ecology in theoretical and practical ecologists. On one hand, theoretical ecology is usually concerned with illustrating suspected dynamical motives, maybe estimating the quasi-stationary distribution and estimate quantities at the quasi-stationary distribution, but not so much with estimating real state or real parameter values, simply because there is no real system at hand usually, or because it's the topic is more proof of concept study. However, in practical ecology, usually a case study is built around a real model at hand, and one wants to estimate parameters, current states, and predictions at these current states. Either way, this splitting means that the typical theory experiment correspondence often remains rather qualitative. So beyond this cultural issue, there's a more tangible issue that feeds into it, namely that there's the computational implementation of simulation and prediction is drastically different for stochastic models. It's not so for deterministic ones, but for stochastic models, those are two very different things. So let's to talk about prediction now. Let's settle on a notion of prediction in general. So by prediction, I mean that we observe a trajectory of the model or of the system only indirectly through observations YL of some derived quantity Y that are taken at discrete observation times TL. So the model evolves in continuous time, but the observations are taken at discrete observation times. An example is provided by flow cytometry. So here, taxa, for example, microbes swimming in a liquid medium, are swimming in liquid medium, and the medium is also laced with counting beads. Then it is focused into a narrow beam that passes through a laser. The laser is scattered, and the scattering signals are counted, and taxa and beads identified. This is repeated until a target amount of beads is reached, and then the counted abundances are taken to estimate the population. And typically, not all taxa can be distinguished in this way, so these Y variables are usually lower dimensional than the X variables. Then once the state is estimated, one usually wants to predict another quality ZL that depends on the current state XTL. An example would be the estimated time to extinction of some selected taxons when it starts from the initial state XTL. So more formally, in the Bayesian setting, this boils down to the following procedure. One has to derive the filtering distribution Xi-L, which is the conditional distribution after the observation time series has been received. And then one conditions the distribution of the ZL quantity on this one. We will be concerned with the first part of this, with the Bayesian filtering. And in particularly for long data series, the only way to computationally accomplish this is by recursive Bayesian filtering, meaning that one sets a prior Xi0, and then in each time step propagates the current filtering distribution Xi-L-1 to Xi-L hat using the probability law of the state process, and then subsequently conditions this on the next observation, resulting in the next filter distribution. And the natural choice for this Xi0 is the quasi-stationary distribution, which represents the minimal prior knowledge that all taxa are present in the population, but not to what quantities they are present. So first computational issue with this was a very idealized algorithm, right? So the first computational issue with this is to estimate the quasi-stationary distribution that works as an initial state here. And this can be accomplished by considering the Fleming-VO process associated to the Markovian interaction network, which basically runs many particles, each particle being an instance of the continuous time Markov chain of the underlying model. And they run independently until one of them is absorbed at the boundary, at which point it gets randomly, its state gets randomly reset to one of the others. So it is plausible that this process would have the same stationary mean distribution as the underlying single particle process, so to speak, conditional on non-extinction. But in general, it is not so clear. However, for the case of Markovian interaction networks, there's an interesting article from 21 by Champagnard and Villemonet that shows interesting sufficient Forster-Lyapunov criteria that can be easily checked for the case of Markovian interaction networks, and by which it can be established that the quasi-stationary distribution first exists and is unique, and also that the Fleming-Vio process converges to it. So just for completeness, such Forster-Lyapunov criteria work in this way that one has basically to guarantee that the particles don't escape to infinity or are unlikely to escape to infinity. So one has to check whether at some large distance from the origin, the particles are more likely to get closer to the origin than go farther out. So that's how these criteria usually work. The second computational issue, once one has estimated the initial prior, is to propagate according to the process of the state, according to a law of the state process. Again, the exact propagation would involve solving the master equation of the process, also known as the Kolmogorov-Forward equation. And we don't have to go into the details of this equation, but suffice it to say that it is an ordinary differential equation for the measured psi, so for probability distribution psi, and it is usually intractable, as these measures live in an infinite dimensional space, technically speaking. However, one can adapt the Fleming-Vio process with weighted particles to propagate this. Namely, one approximates each filter distribution as a weighted point distribution, and simply propagates the points by the Fleming-Vio process. This leads to what I call the Fleming-Vio filter that is also implemented in software. A more advanced method that I'm still working on is the Lna Mixture Filter. It makes each particle into a Gaussian distribution and uses the linear noise approximation of the continuous time Markov chain to propagate those Gaussians. So this has been applied in other areas than ecology, and it has been shown to be superior to a simple particle filter. The reason seems to be that the support of each particle filter distribution is just of measure 0, while the Lna mixture filter distributions, in a sense, cover all of state space. So it's more unlikely filter degeneracy is less of an issue there. So far, I only talked about state estimation. So what about parameter estimation? Just a few words about this. Here we would identify a Markovian interaction network with a parameter Q in some parameter space. For example, in the mass action kinetics example before, the parameter Q would contain the values of the reaction rate constants. Then we would consider a source model Q0, which is a point in this parameter space, and a weighted ensemble of inference candidate models Qn with weights Wn. And then we would run another particle filter for weights and parameters on top of the state filter. So we would start with an initial weighted ensemble, and then we would first derive the quasi-stationary distributions, or estimate the quasi-stationary distributions of each Qn, and collect them into a vector boldface psi0. Then we would retrieve an observation time series Y1L and do two things. First, filter this psi0 to psi L as per the rules of the state filter, and at the same time apply Bayesian conditioning to the weights corresponding to how well they in this data series Y1L managed to predict the next value, or how good the model Qn respectively managed to predict the next value. And then in the last step, and there's much room to play with here, the parameters Q have to be modified according to some Markov process on state space. So there's of course various ways of doing this, of outlining a Markov process of state space that leads to a different inference algorithm here. And then this is done as long as one pleases. This loop is repeated. In the end, we end up with the weighted ensemble, and what has to be checked is whether this is able to approximate the source model Q0 well or not. So that's the plan. Let's now see how well this or what works as of now. So this experimental design software that tries to do this all automatically should have the task to evaluate state and parameter estimability, ideally prior to experimentation, and then also perform as the state and parameter estimation for a given data series. But really the first task is the difficult one. It should be coded in a modular Python architecture, so that, and in particular, it should it should work with data types that are very close to the mathematical formalism, so that if a mathematical or theoretical ecologist or some other person inclined to develop the system wants to incorporate their methods as software components, it should be just as translating mathematics to code with very closely corresponding data types corresponding to the objects of stochastic calculus. And by this token, it should become an extensible open source project. On the other hand, it should have a simple user interface where a practical ecologist can just input his or her model and check for parameter and state estimability. And of course, it should be able to process any given network. So let's say what one has to do until now. It has no user interface until now, so we have to do this in code. So we set the taxa H1 to H1, H2, P1, P2, and then we prepare a list of interactions. And for each interaction, we give the interactants. So here 1, 0, 0, 0, and the products of the interaction 2, 0, 0, 0. So this is asexual reproduction as before. And the kinetic law is mass action. We give a rate constant. And then we can make an instance of the interaction Python class that is part of the platform. By giving it this data, it creates an interaction object, and we collect these in the interactions list. We set the volume, which was the K parameter before, and then we create an instance of the Markovian interaction network class that gets as parameters the interactions and the volume, and then the network is built. Then we can also specify the observable. Here I implemented so far this what I call beat counting observation, which mimics what happens in the flow cytometry example before, implements the same statistics. So here we have to let it know what taxa are subsumed in the same measurement. So H1 and H2 are both cannot be distinguished, so they both map to H, and P1, P2 both map to P. We give the duration of observation at the time step and pass this and create an instance of beat counting observable, which is then our observable. So then all the data is this is all specified now. And in as a first impression, we can plot the interaction network. So this is the same predator-prey network host-parasite network as before. We can plot trajectories by creating an instance of continuous time Markov chain, which takes the network and has then a continuous time Markov chain, or is a continuous time Markov chain that has certain methods. For example, we can set it up with an initial state and initial time and run the method sample trajectory until an end time. It then stores the trajectory into the attribute ctmc.trajectory, and we can plot this in 1 or 2 dimensions. We can do the same for the observable trajectory. Again, the attribute ctmc trajectory is given to the method map trajectory of the observable instance, so that simply maps the whole trajectory according to the observable. And we can also plot it. We can, in the same way, create an instance of the Fleming-Biot process, giving it the Markovian interaction network and the particles, provide some seed states, and again sample a trajectory. This is then saved to a directory on the hard disk because it's a rather large file. And then we can aggregate the QSD from this and again plot it. And this was used to do all the plots in the article before. So then to assess state estimability, again, just a few words. The idea is to sample an initial source state from the quasi-stationary distribution, map it to an observed trajectory, initialize the Fleming-Biot filter at the QSD, and filter it according to YL. Repeat this many times and produce filter statistics. As of now, there are no filter statistics yet, but there is a visualization of how the filter works. If I can find it. No, can't find it. Here. Seems not to work on this computer. Too bad. Maybe, I don't know if it is if this computer has VLC. Where? There. Yeah. Right. Okay, better say no. So this is the in red we see the true state of that the inference doesn't know, and blue is the filter distributions. So it seems to lose it intermittently, but then find it again. So these are the axes here are the hosts and the parasites. So the observables in this case are hosts aggregated and parasites aggregated. So the model does not know this where the point is with respect to parasite 1 and parasite 2. And the red dot is where the source model actually is, from which the data was produced, and the blue distribution is what where the filter thinks it is. In this space of hosts and parasites. So the red, in a sense, from the red dot, the observations were produced, but they are in another space, and blue is the result of the inference. So it seems to intermittently lose it, but then it finds it again. And of course, this filter still needs to be improved. And as I suspected, the particle filter is not really up to it. I mean, this is with 1,000 particles. Usually these particle filters are run with vastly more than 1,000 particles. So at some point it might work. But I suspect that with the Lna mixture filter, it already works at this size, even with less particles, probably. At least that's what other works have shown that are from other fields than ecology. So here we have arrived at the end of the presentation. I'll drop this, and I like to thank my collaborators Carlos Melian and Gianmarco Palamara, who for many valuable discussions, and particularly for confronting me a lot with all the customs and so on, and the ways of working in ecology that I wasn't familiar before, coming from mathematical physics originally. So thanks a lot for the good collaboration. And so we have arrived at the discussion, I suppose. Thank you.
So, if anyone has questions, also you can they can unmute themselves. You can unmute yourself and hello, and ask questions if you have any. And if not, we'll ask some here. No? You have.
Juan. Juan?
Okay, yes.
Yes, you can talk.
Well, just to, I have a maybe later question, but if there is some question in the audience there, it would be great to repeat the question, Leo, because we don't hear right from the audience. So yes, if people ask questions, that would be great. Yeah, thank you.
That, yes.
I have a question. Well, I become lost at some moments because of the nomenclature. I think that you are doing very interesting things in a language which is well, all of us are physicists, I think, and we so you are using a nomenclature which is not the one we are used to. But I will ask you a little bit a few things. For example, the Fleming-Biot process. I understand that it's just running several simulations with the same parameters. I mean, it's just doing what we call different realizations of the same stochastic process. Is this true?
Yes. So the question was about the Fleming-Biot process, whether this just runs several realizations of the same process, and this is true. But the point is that that when they are absorbed at the boundary, they get reset to another one, right? So in principle, they are dependent on each. They are not independent totally because they are joined at some points, right?
So my question is, what happens when you reset them randomly? Randomly, what, uniformly everywhere, or you have some rule to reset them somewhere in particular, or so what is the rule to reset them when they are absorbed?
They are reset randomly at the locations of one of the remaining particles.
So they copy the location of one of the remaining particles.
Yes, and in the Fleming-Biot filter, there also the probability weight is copied, so they are just identified with one of the remaining particles. Yes.
And I have a second question. Is in the last part when you change. In the example you have shown on the red dot followed by the blue cloud, I don't. Are you changing the parameters every time you run at every time step? The parameters are updated. I don't understand. What do you mean by predict? So you have your data, but it's partial because you have 4 variables, but you only observe partially 2 of them. And then you want to have a stochastic process that is similar to your data, and then it's not exactly equal. But then what do you do with the parameters of the inferred stochastic process? Is updated every time step, or is the same all time step? I haven't understood what you do with it.
So in the case of this video that I showed in the end, that's always the same parameter. There, the question is simply whether the filter that knows only about the 2-dimensional observables of the actual state can infer the full state from this. when the full state moves around quite a lot. I mean, this is rather trivial when the state is confined to a small area, but in this model, the source state moves around a lot, and the question is whether even under the ideal assumption that one knows the correct parameter values of the source model, which is also not true in practice, but even if that was true, the question is if it is then possible to infer the true state. And if this question is already an answer to the negative, then would be definitely a point against applying this specific model for in experimental trials, right? Because it is, if one is interested in finding out the true state or some predictor that depends on the whole true state. Because if it doesn't even work when one knows the correct parameters, it's very unlikely that it will work when one has wrong parameters, right?
So I didn't understand. Given the parameters, if there's a problem in finding the true state, what do you mean by true state?
The current state of the model. So the model has a current state that lives in a 4-dimensional space, right? Mm-hmm. But the observations are 2-dimensional. So the current state of the model cannot simply is not a function of the observation. But it can be, but ostensibly it can be improved when several observations in sequence are used, right? So that's kind of the point of it.
So I had a sort of, I guess, more philosophical question. I don't know. So are you in this whole approach? Mm-hmm. Is this sort of restricted to relatively simple models of this kind of, okay, I have a handful of species and a handful of reactions? Or can I do this kind of upscale, scale this up, right? And I don't know.
I think so it is two ways of upscaling, right? Either large populations or more species and more interactions. So the upscaling with respect to larger populations, that should not be a problem once the Gaussian mixture filter is implemented. For now, this would also be a problem, but for many species and many interactions, in principle, it can be done. But it's, I mean, the issue is really the dimension of the state space, right? So usually with particle filtering, usually the algorithmic complexity here, or anyway the resources needed for this scale exponentially with the dimension of the state space. So this has to be.
Yeah, in the back, yes, but the back. So because the background you gave is that somehow this is an effort to bring data and models closer to each other, right? Mm. So presumably, ultimately, you want to apply this to real data.
Yeah.
And then, but if the models that you can use are relatively stylized, would that make applied ecologists happy? Or would they then say, well, okay, you have fitted your model to this data, but I don't believe in the model or in the class of models that you have admitted, right?
Yeah.
So that's the more long-term philosophy that
Yeah.
So I mean, don't get me wrong, right? I applaud the. So it's just sort of going back to the beginning of your talk. I'm not entirely sure this will solve or address the problem, right?
Well, it might address the problem that models are. Even though one shouldn't trust in the models, one still does, right? It's rather a method to falsify models that are not that will not be able to give good predictions. I mean, if the Markovian interaction network model, the Mesoscopic model, is not able to good predict doesn't lend itself to good predictions at the resolutions where observations are made anyway, then this platform will merely reveal that, right? It will not. Then it's rather a model diagnosis tool than a modeling tool itself, because the model is the underlying mesoscopic model, right? The question is whether this is should be trusted or not.
Then I had sorry.
Yeah,
so there was at the beginning you said this whole approach is restricted to well-mixed interactions. Yeah. but you, I mean, what you, the simulation method that you have described at the beginning, what you call Markovian interaction, we would call this the Gillespie algorithm.
Yes.
And that can be done for spatial systems, right? So there's no problem to doing that in spatial systems. You just divide your, I mean, you just have reactions at different locations. So there is, in principle, no problem.
You mean a finite or a discrete set of locations, or no, this would be no problem indeed.
This is just introducing more species each.
Exactly. The problem comes when there's a continuous location variable, right? Then it gets more. But
also you have a very high dimensional state space.
Right. Yeah, but in principle, this is not like a discrete location space. Is in principle no problem.
So I have another question. So with the, maybe I didn't understand everything for the last video. So the filter knows the model and the parameters.
Yes.
Okay.
But it does not know the current state, but it knows the rest. Yeah.
Okay. So when you were saying that you can do also parameter estimation, then you know the structure also of the model, but you don't know the numbers that come into each interaction.
Exactly.
Okay.
Yeah.
And you know the state, supposedly.
No, you also don't know the state. So in this parameter estimation, on the level of parameter estimation, you're trying to estimate both at the same time then internal states and parameters of the model. But the model structure is fixed still at that.
So could this be thought of also as a building block to generate models and say, okay, I will try different structures of models with the data that I have, and based on some kind of quality measure, I say, okay, I go from one model to another, and then you use this as a building block to construct different models.
Yes, that would be kind of a long-term objective of this. And also, I mean, just from a theoretical point of view, that also has interesting ramifications for investigating the structure of model space itself, right? So that's usually not done so much in these kinds of stuff, with these kinds of inference frameworks. But that would be an interesting point where I think even these ecological applications could lead to sort of a bit new mathematical frameworks, because these model spaces are usually so I did some work in the past on that, which is on the archive somewhere, but there's so they are usually so they are built from blocks, as you say, and each block is in a sense the quotient of a manifold with corners by a finite group. So these are all things that are investigated in mathematics have been for a long time, but not quite in this way of combining discrete structures with continuous parameter manifolds. And so I think there is potential there to investigate.
So if someone else has a question.
Yes, I have one. Okay. Yes.
Go on.
Leo, it's about the formal prediction problem. So the part of propagation according to the state process law. So I was thinking, so is there any way to quantify analytically when you do these realizations using this machinery? There should be some property, at least for the simplest scenario where, for example, the interaction coefficients in the Markovian interaction network and the connection to time series or the extinction times. So something really simple that can be analytically easy to obtain to compare with more complex scenarios. Is there any because now correct me if I'm wrong, we could predict that the stronger interactions in the realizations, the stronger the fluctuations. But maybe I'm wrong here, because maybe the jumping process is independent of the strength of the coefficients in the realizations. Do you have any intuition around this?
So say again your hypothesis at the end. The stronger the interactions.
Yes, then the jumping process. So essentially the time series. Yeah, if you analyze this time series, you have a stronger fluctuations, and then extinction probabilities also go up. But so is there any analytical derivation around this?
So this seems reasonable what you're saying. Also, when the system size becomes lower, there's also a larger probability of extinction. When it becomes when the system size becomes rather large, extinction is a rare event. And but if it's small, then even the rare events are not so rare, stochastically speaking, right? But to do this analytically, that is quite difficult. I mean, there's really in closed form solutions that pretty much only works in one effective dimension. 2 dimensions if you have maybe you restrict to you fix some variable combinations to some, but effectively in 1 dimension, let's say it works. Some approximate methods, as far as I know, about extinction times have been obtained using the WKB formalism that comes from physics as well. So, but this is very incipient, this work. But I think it would be difficult to compare this with this model, because both are kind of in its infancy, right? There is some analytical work of this, but it's still, even with this WKB formalism, where I've seen it, it's also been done only in 2-dimensional systems. So I think as soon as there are just a few more dimensions, that's quite difficult usually.
Yeah, thank you, Leo.
So, any more questions?
Yeah, I have a question. Do you hear me?
Yes. I
yes.
can hear you, Jamal.
Okay, so thanks for the nice talk. You use a formalism borrowed from chemical kinetics. Also, these tools have been developed for the Gillespie algorithm has been developed originally for chemical physics. So my question is, what are the advantages and the disadvantages of this analogy, and until which level you see the potential of using this formalism to describe such complex systems like ecological systems?
Sorry, I didn't quite understand the advantage of this.
The advantages and the disadvantages of using this formalism.
Yes.
And until which level you can use this analogy to describe these complex systems, complex ecological systems.
Yes, I see. Advantages as compared to the ODE-based approach are definitely that the system volumes that have to be well mixed as an assumption can be much lower in this case. But what's still required is that, or what should still hold, so that this makes sense, is that the interaction events are really very short events in time, right? So, for example, I guess for predation and stuff like that sounds like this is a short event. But if, for example, in the predator-prey model, in this simplistic predator-prey model, that an individual prey individual dies and the predator individual is born at the same time. This is of course not how it works, right? So this also when these models have been applied to mutualism in some few cases that I heard, but also there I think if 2 species interact in a mutually beneficent way, the advantages to the 2 species might come at different points in time from the interaction, really, right? I guess this does have a lot of potential for this approach for a more fine-grained temporal analysis of interactions in populations, but one has to take seriously that the points in time where one has to kind of decode the interactions in an appropriate way. Yeah, but definitely this is a point that cannot be captured by the deterministic macroscopic limits. So, yeah, I think this, and also one thing that's so in chemical kinetics, this is generally confined to two individual interactions, simply because the molecular statistics does not allow meeting of more than two at one time, like encountering of two molecules at one time. This has to be a sequence of reactions there. So this is a potential. This is a generalization of it ultimately. That is that has to be looked upon closely, whether this is justified in certain cases at hand.
Thank you very much.
Thank you. More questions? If not, let's thank again Leo for the fantastic talk.
Thank you. And thanks for having me here.
Thank you. You know how to open this? Okay.